Welcome to The Explainer. Today we're doing a high-level review of Chemistry Chapter 12 on thermodynamics. We're going to connect all the dots, pull together all the big ideas so you can really see how everything fits together. Okay, let's just dive right in. I want you to picture something like a geyser. It's this amazing, powerful thing that just happens. But why? Why does a hot cup of coffee always cool down and never just spontaneously get hotter? It's pretty clear that nature has a preferred direction for things, and the huge question for us is, can we actually predict that direction? And the answer is a big, resounding yes. That's really the power of what we're talking about here. It's not just about understanding what can happen, but about being able to predict what will happen under certain conditions. And the tool that gives us this predictive superpower, that's thermodynamics. It's basically the rulebook for how energy and work behave in all sorts of chemical and physical processes. But, before we can really use this rulebook, we've got to learn the language, right? So let's take a quick look at some of the essential vocabulary for this chapter. So this first batch of terms, what's really interesting is how they all set the stage for us to measure change, disorder, and basically the direction that things want to go. Go ahead and take a second to look these over. The two you really want to lock in are entropy and Gibbs free energy. These are pretty much the central characters in our story today. All right, let's move on. To make all these concepts truly useful for comparing different reactions, we've got to make sure we're all playing by the same rules. We need to standardize things. So the most important thing to notice here is that little circle symbol we call the not symbol. Whenever you see that, it just means standard conditions. This is what lets us compare different reactions fairly. So for example, if you see delta S naught, you'd say delta S naught. Okay, so now that we have the vocabulary down, let's see how these words get translated into the mathematical relationships we can actually use for our predictions. The first two equations here give us two different ways of looking at entropy. The first one, the thermodynamic way, connects the change in entropy, that's delta S, to heat and temperature. The second one, the statistical view, connects entropy to the number of possible arrangements, or microstates. It's really cool. One is a big picture view, the other is a microscopic view. And this is how we make it practical. This brilliantly shows how we can calculate the total entropy change for a reaction just by taking the standard values for all the products and subtracting the values for all the reactants. It's kind of like chemical bookkeeping. Now, this one looks super simple, but its scope is just massive. It's telling us that the total entropy change of the entire universe is just the sum of the change that happens in our system, our little beaker, and the change in everything else, the surroundings. All right, so with our new vocabulary and equations, let's start connecting them to the really big ideas, starting with this concept of spontaneity. The key takeaway here is that spontaneity is all about whether a process can happen on its own, without a constant push from the outside. But, and this is super important, spontaneous does not mean fast. Resting is spontaneous, but it can take forever. It just means it's the direction nature prefers to go. So entropy isn't just about chaos and disorder, even though you hear that a lot. A much better way to think about it is as a measure of dispersal. It's a quantifiable way of looking at how spread out the energy and matter in a system can be. The more ways it can be arranged, the higher the entropy. And this comparison makes the trend really clear. As particles get more freedom to move around, entropy generally goes up. It just makes sense, right? A gas has way more ways to arrange its particles than a tightly packed solid does. Let's move on and see how these concepts are actually formalized into some really fundamental laws that govern, everything. These two laws are huge. The second law gives us the ultimate rule for spontaneity. Any spontaneous process has to increase the total entropy of the universe. And the third law gives us a definitive starting line, a perfect baseline for entropy itself. Okay, so how do we predict if something is spontaneous by only looking at our system? We can't exactly measure the entropy of the entire universe every time we run a reaction. That's where free energy comes in to save the day. This is it. This is the ultimate predictor we've been building up to. It's a single value that tells us if a reaction will proceed on its own. And the rule couldn't be simpler. If the change in Gibbs free energy, delta G, is negative, the process is spontaneous. It's that easy. And this equation right here, it just illustrates that relationship perfectly. The change in free energy, delta G, is this fascinating balance between the change in heat, which is delta H, and the change in entropy, that delta S term, which gets more important as temperature goes up. And that's our wrap-up of Chapter 12. Hopefully, this helps you connect all the key concepts, the terms, and the equations. We've basically built a tool that lets us predict the future of chemical reactions, which is pretty amazing when you think about it.